Hello guys, this is Physics 1 with Nicole,
Eric Smith,
Deja Tool,
and Dwayne Washington.
and today we're going to be explaining and working out problems over Chapter 10, Rotational Motion. So I'm going to be taking a question from the homework that was assigned, question 3, and the equation that I'll be using is theta equals rho naught times time plus 1/2 alpha times time squared plus theta naught. So the problem that I'll be using is question 3. It says, initially a wheel is rotating about a fixed axis at a constant angular deceleration of 0.5 radians, which is going to be used as our alpha. Negative 0.5 radian times second squared, and has an angular velocity of 0 radians per second and an angular position of 7.3. The 7.3 is going to be our theta naught, and it is also a radian. And then the last part of it, what is the angular position of the wheel after 4 seconds? So the t is going to be 4 seconds. So to write it out again, the equation is theta equals rho naught times time alpha t squared, oh my bad, sorry, plus 1/2 alpha t squared plus theta naught. So in the problem it stated that the velocity of 0 radians, so we're going to write that equals radians of 0 times seconds. And then we're going to take the time, which is 4 seconds. And then after that, we're going to do the second part of the equation, which is 1/2 alpha t squared plus theta naught. So the 1/2, I'm going to plus it, 1/2 times our alpha, which is negative 0.5 radians seconds squared, times our time, which is the 4 seconds. And this time we're going to square it. And then plus our theta naught, which is 7.3 radians. And let me grab a calculator to do the calculation. So we're going to take the 1/2 times the negative 0.5 radians second squared times our 4 seconds squared also, plus the 7.3 from the theta naught, which comes out to 3.3, and it is in radians. And that is the angular position.
How you doing? I am Dwayne. Let's get into our next problem. So it says, find the magnitude of torque produced by a 4.9 force applied to a door at a perpendicular distance of 0.48 meters from the hinge. Well, let's go look at that. Follow me. Here we have a door, right? And it said that they applied a force, which is me, of 4.9 newtons. And they applied it 0.48 meters from the hinges. So this is the hinge. Let's say this is about 4.8. Well, I'm going to apply a force, right? The door opens, right? Which proves that the door will actually open. There's work actually being done. So let's go back. So let's talk about the stuff that we know, right? We know the force, which is F, is equal to 4.9 newtons, right? And we also know the distance, the distance of where the force was applied. I applied the force 0.48 meters from the door, right? It also says that the force was applied perpendicular, right? Which lets me know that my angle is a 90-degree angle, right? So let's do the work. So T, which is torque, equals my force times distance sine of theta, right? So now we just need to plug it in. So it will be 4.9 newtons, right, times our distance, which is 0.48 meters, right, times sine of 90 degrees, right? When you get that, it's going to be newtons times meters, so you should get 2.352 newtons meters. And there you have it.
Hi, I'm Eric Smith, and I'm going to show you how to calculate the moment of inertia of a solid sphere about an axis tangent to its surface. This is the equation for the moment of inertia. So for this problem, I'm going to have to do the moment of inertia plus the mass times radius squared of the ball. All right, so there's a figurative 1 in front of there. So when I add these two together, I get 7/5 m r to the square. And that leaves me with 7/5 times 6.69 kg times 7.66 meters squared. And that final answer leaves me with 549.55 kg times m squared.
Okay, I'm Deja Tool, and my problem will be showing you the network on an accelerating propeller. So it says the network done when accelerating a propeller from rest at an angular speed of 106 radian per second is 2,532.8 joules. Okay, so first we have, and it's asking what is the moment of inertia for the propeller. So we have our work, which is 2,537.8 joules. And we also have our angular speed, which is equal to 106 radians per second. And since it's starting at rest, the initial radians per second is 0. Our initial angular speed. So we have the work, the net work is equal to delta K times E, which is also equal to 1/2 the inertia of your angular speed squared, the final, minus the squared initial, which also equals to 1/2 angular angular speed squared final. Therefore, let's see, which is looking for your inertia. Therefore, you rearrange your equation to find inertia, which equals 2 times the work, net work of course, all over your angular speed final squared. So with that, you plug in your things. And I will equal to 2 times the work, which is 2,537.8 joules, all over your angular speed, which is 106 radians squared. And with that, you plug it in, and you should get 0.455727 kilograms times meters squared.